Okay, so I think we can get started now. So again, good morning or good afternoon, everybody. Welcome to the first session of the day, which is going to be on thermomechanical properties. So this is how you can calculate thermomechanical properties with AFLOW using the AFLOW-AEL and AFLOW-AGL modules. So this is the AFLOW-AEL. So this is AFLOW. So this is the automatic elasticity library, and this is the automatic Gibbs library. So this one is a Debye-Grüneisen model, and this one is for elastic constants. So why are we interested in thermal and mechanical properties of materials? Well, they're important for a variety of applications, particularly things like, so for example, for mechanical properties, you might want things that are super hard wear resistant coatings. For things like machine tools, so you might want cutting blades. So cutting implements for machining, you might want drill bits for either for, again, for machining or for things like mining. Then you might also want, so for thermal properties and mechanical properties, you might want things like thermal barrier coatings for energy and aerospace. So here, if you have a jet engine or a gas turbine engine, so this has a very hot exhaust. The hot exhaust will have things like so unburnt combustion, unburnt fuel, oxygen, combustion products like water vapor, high temperature water vapor, all of which can be very reactive. So these can corrode these turbine blades. Also, you want, the higher the temperature you have, the more efficient your engine is going to be. So you want to have try and increase the temperature that your engine operates at. In order to do that, therefore, to protect the turbine blades, to stop them from melting or deforming or corroding, you want to use these thermal and environmental barrier coatings. So for these thermal, so first of all, you want to have something that has low thermal conductivity to protect the underlying turbine blade. But you also want something that's reasonably mechanically strong, because if you have something very soft or porous, it's going to be damaged quite easily. So finally, another example here will be something like heat sinks for advanced electronics. Here you have, if you want to have something that's an electrical insulator, but a thermal conductor. So you can't just use metals, which also have high thermal conductivity, but here you want to have something that's high lattice thermal conductivity specifically. There are other applications for things where you want to know thermal conductivity. So you have things like thermoelectrics, for example. You also wanted to use mechanical properties are also quite important for things like biomedical implants. So if you think of things like hip replacements, where you want to match the mechanical properties of bone, so you get similar behavior. Okay, so in order to do this, especially to calculate mechanical properties, what we start is with elastic properties. So with what's called the stress-strain response. So the idea is if you have a real material, you apply a certain stress to that material. You want to know how much is going to deform, what the strain is going to be on that material. So what the stress-strain response is going to be. So to calculate this, what we do in practice is that we apply a set of strains, so we call normal strains. So this is just stretching the material in one direction. And you have shear strain, so where you stretch like this. So you stretch, so the stress is applied, a shear stress like this. So in our case, so in order to calculate all these elastic properties, you need to do it in all three independent directions. So we apply 4 strains in each of these independent directions to make sure we're actually getting a linear stress-strain response. And in this way, this also allows it makes sure that you can eliminate noise. You don't have to worry about whether the material is fully relaxed, because so you're not necessarily taking the difference from 0, but you're taking the difference from +1 to -1. In AEL, so the default is to apply a maximum applied strain of 1%. So 1% elongation of the cell, for example. Okay. So then what you do then is you obtain what's called the elastic constant. So this elastic stiffness tensor. So this is in practice, this is actually a 3 by 3 by 3 by 3 matrix, but this has certain symmetries and which allow it to be represented as essentially a 6 by 6 matrix. So this is what's called the Voigt notation. So these 1 to 3 represent the normal strains, and these represent the shear strains. So yeah, normal stress strain response, and this is the shear stress strain response, and this is a combination of the two. These are on the off diagonals. So to give you an example, if we apply a strain 1, 1, so this is a normal strain essentially along the x direction. You then calculate the stress tensor, so you get the full stress tensor from a DFT calculation. So in this case, VASP will give you the full stress tensor. Then for each one of those, you can obtain this C11, C2, C12, and so on. So you can obtain this full column of the elastic tensor. And so then you apply all of these different sets of strains, and then you can, from this, you can calculate your stress tensor. So essentially you'll have a set of strains here, you'll get a set of stresses, then you fit this stress strain, and then the slope is just going to give you your elastic constant. So then once you have your elastic constants, you can use these to calculate what the different elastic moduli. So things like just to mention, we also have this, what's called this compliance tensor, so it's Sij, and this is the inverse of this stiffness tensor, Cij. So you invert this matrix here, you get this compliance tensor. Okay, so once you have these calculated, once you have the elastic constants and this compliance tensor elements, you can calculate what the elastic moduli, so things like the bulk modulus, which is basically if you apply a certain pressure, how much it will compress, the material will compress or expand depending on a uniform pressure on the surfaces. So here we have two different approximations. We have what's called the Voigt approximation and the Royce approximation. So the Voigt approximation you get directly from the elastic constants themselves, whereas the Royce approximation you get from the components of this compliance tensor. Okay, so the difference between this, so in the case of the Voigt, this Voigt approximation, this is assuming uniform strain. So the strain is uniform, and the stress is what varies on the different grains. So this is really for a polycrystalline material. So if you have lots of little grains, then it's assuming that the strain on each grain is constant. So each grain has the same strain, but different stresses, and the stress is supported in parallel by the grains. And this gives you an upper bound on the bulk modulus. For the Royce approximation, it's the other way around. It assumes that the stress is uniform, so each grain has the same stress, but they have different strains. They can have different strains, and this gives you a lower bound on the bulk modulus. We have similar things for the shear modulus. So the shear modulus, again, is just going to be the response to shear deformation. So if you apply a shear deformation like this to the material, how much is it going to stretch for a given shear stress? Then we can combine the Voigt and Royce approximations to get what's called this Voigt-Royce-Hill average. So this is just the mean of the two. And from this, then we can calculate other elastic properties and mechanical properties. So things like a Poisson ratio. You can also do things like estimate the hardness based on a combination of the bulk and shear modulus. Although this tends to be better for nano hardness, and particularly tends to work better for ceramics than for metals, because in metals you have other types of you have things like slip planes and these sort of things that strongly affect the behavior of the materials. And metals in particular tend to the things like hardness, so the macroscopic elastic properties tend to depend a lot more on what's called the microstructure. So they depend on things like if you have impurities or these sort of things inside the metal, that tends to affect these macroscopic quantities a lot more for metals than it tends to do for ceramics. Okay, so let's keep going with these calculations. Okay, so that's for the elastic constant. So this is for this linear stress strain response. So this is for like essentially zero temperature, very small deformations, what kind of elastic response you get. But if you have to look at finite temperature, you need to look at somewhat larger responses in the volume. So there's different ways you can do this. Dr. Esters tomorrow and Dr. Smolyanyuk will be talking more about how you actually directly calculate the phonon dispersion, both in the harmonic and the quasi-harmonic approximations. But here we're going to do the very simplest approximation that we've implemented in AFLOW, which is a Debye-Grüneisen model. So in this case, we have we start from different volume unit cells. So you take your calculation cell, you expand and compress the volume of the unit cell. You calculate the energies of these unit cells as a function of the volume. So you get this basically energy volume curve. You then fit this either by a polynomial or to an equation of state. So like this. So this gives you, so from this, you effectively get back some kind of analytic equation. From this, you can then get things like the bulk modulus, either by taking these derivatives or by directly from these equations of state will give you the bulk modulus as a function of volume. Once you have the bulk modulus as a function of volume, then you can estimate the Debye temperature from this expression here. So this here again is your bulk modulus as a function of volume. So this is sort of based on an expression for the speed of sound in a material. Then we also have this term here, which is a function of the Poisson ratio nu. So one of the things we can do with the AEL and AGL, because they're now a combined workflow within AFLOW, and this is sort of one of the advantages of having these sort of integrated frameworks, is that way you can set up a workflow that will automatically calculate the Poisson ratio from AEL and use that value inside the inside this AGL, inside this Debye-Grüneisen model. So once we have this Debye temperature, we can then calculate the vibrational free component of the free energy using this expression here. And then you can add these terms together. So you have the energy as a function of volume you got from your initial DFT calculations. You have your vibrational energy as a function of volume and of temperature. And then you can add on this pressure volume term. And this will give you your Gibbs free energy as a function of volume, pressure, and temperature. So again, if you fit this at a given pressure temperature value, you again fit the Gibbs free energy as a function of volume, you can find the equilibrium volume for that pressure and temperature. Once you have that equilibrium volume, you can then get things like the Debye temperature at the equilibrium volume. You can get things like the Grüneisen parameter, which I think Dr. Smoljaniuk will talk a bit more about tomorrow, but it's sort of a measure of how the thermal properties vary as a function of volume, and hence as a function of temperature. And this is where the real quasi-harmonic part of the approximation comes in. You can calculate things like what's called the acoustic Debye temperature. So this is the Debye temperature if we only assume that the acoustic phonon modes are contributing. So these are the lowest frequency vibrational modes. So if we can approximate this acoustic Debye temperature by taking 1 over the cube root of the number of atoms per cell. So finally, you can use this expression here. So this is based on what's called the Liebowitz-Schlömann model, and this is further developed by Slack to get this expression here, which is an approximation for the lattice thermal conductivity at the acoustic Debye temperature. And then you can also estimate the lattice conductivity at other temperatures by using this 1 over T approximation for the variation of the lattice thermal conductivity with temperature. Okay, so in practice, if we want to see how well this actually works. So here on the left-hand slide, in the left plot, we have the Debye temperature. So here's the experimental values that are reported in the literature. On the x-axis, on the y-axis, we have the ones we've calculated with our Debye model. You can see that the agreement is mostly pretty good for materials with these types of structures. So these are common, reasonably hard materials. On the right, you can see that we have more of a spread. So here we have, again, here's the lattice thermal conductivity at 300 Kelvin. Again, we have the experimental values on the x-axis and the calculations on the y-axis. You can see there's a bit more of a spread. The reason for this is that the Grüneisen parameter is actually quite a difficult property to get accurately. And because of this, you tend to overestimate the Grüneisen parameter, which in turn means you tend to underestimate the lattice thermal conductivity. But you can see one thing, you can see that we tend to get quantitatively, the values aren't super accurate. Qualitatively, we tend to get the right trend. And because of this, it's reasonably useful as a rapid screening model to identify which materials might have a very high or very low thermal conductivity that we can then investigate in more detail using more sophisticated and more computationally demanding methods, such as the ones that will be described tomorrow. So here are the correlation with the experimental results. So this is the Pearson correlation, as you have the order of about 0.9. Using the AEL Poisson ratio, so instead of using an approximation, so there's two different choices. You can have what's called this default value. If you don't know what the Poisson ratio is, of 0.25, which is sort of in the middle of the range of Poisson ratios. It's called the Cauchy ratio. And that's, but using the one from AEL by comparison, so the actual calculated value improves the correlation by about 5%. And there, in general, this method, while it doesn't give you always give you quantitatively accurate results, it does tend to be, it is useful for rapid screening of thermal properties because it tends to get reasonably accurate trends. Okay, let's talk a bit more detail about the actual workflow itself, so the actual software. The combined workflow, it's now been run for about 6,000 materials on the AFLOW database. So if you go to aflow.org, you'll see this in the list of, in the box at the top with a different property, number of different properties. You'll see that we have elastic and thermal properties. The data is accessible online at aflow.org both by the REST API and by the AFLOW search API that Dr. Estes will talk about in the next session. So here are some of the relevant keywords. So you've got this bulk AEL _ bulk _ modulus _ VRH, AL _ shear _ modulus _ VRH. And then for the thermal properties, you've got things like AGL _ Debye, AGL _ Grüneisen, etc. And Dr. Estes is going to, I think he's going to do some examples and actually using the AFLOW search API to actually find materials with specific width, like find a material with the highest bulk modulus or these kind of things, which you can do with our database. So let me just also show you briefly some online features. So if we go to the web page, aflow.org web page, so here you can see that the current number of elastic properties and thermal properties. We also have elastic and thermal property search. So for example, if we go to the elastic properties, we can see that we basically just get the same search page as normal, except now if we go to the property filters, you can see that various sort of bulk and shear modulus type and Poisson ratio are already populated. So if you search for something, these will already be, these will automatically be shown. Okay, so we have a question. Okay, so the question is, so the difference in the Royce and Voigt values depends on the material and not indicative of the error in our elastic fitting. Yes, that's pretty much correct. It's going to be very material dependent, the difference. Generally speaking, what we find that the Royce is usually a bit more robust. Sorry, the Voigt approximation is usually a bit more robust. For the Royce approximation, especially for the shear modulus, if a material, one of the things that we look for is to make sure that you don't have, like, say, negative values of the shear modulus, of the Royce approximation for the shear modulus. That's one of the things that can actually indicate mechanical instability of the material. So sometimes you actually see negative values for this property, and that's usually a pretty good indicator that the structure is actually unstable. But there are other ways to check if the structure is unstable as well. So if you take, for example, let me show here, and this is one of the things that's done inside the AFLOW output file. Probably I'll show a bit more later as well. If we take our elastic tensor here, if we calculate the eigenvalues of this tensor, if any of these are negative, that's something again that indicates that the material is mechanically unstable. So I hope that answers the question. Okay. Okay, so let's go into the technical details of how to actually run these calculations. So again, we start from our aflow.in file. So the files that Dr. Hicks was going through on Monday. So here we can generate a aflow.in file with AEL switched on. So again, we use our prototypes. So this is the prototype here for the rock salt structure. Here we can decorate with different elements. In this case, we're going to do magnesium oxide, and then we do minus module equals AEL. Similarly, you can generate an aflow.in file with AGL switched on. So again, it's the same example, aflow_proto, our prototype, NGO, and then at module equals AGL. Okay, so then there's, like I mentioned, there's some default parameters, which I'll discuss. And these can be changed by editing the aflow.rc file. So you'll get things like the number of strains, the size of the strains, and so on. So let me actually show this example. So I'll go inside mechanical so that we can actually show this, hopefully. Minus AFLOW proto. AFLOW equals AE underscore CFA 225. And here, one of the things we're going to have to use in the next couple of days is this generate. So let's see if it works without it. Might complain because it might not, because VASP, we don't have access to VASP. No, it didn't complain, okay. But we'll see later, because we don't have access to VASP on this virtual machine, there are some extra flags that you sometimes have to use if you want to run some things, because otherwise it will complain because it automatically tries to look for the pseudo potential files, and if it doesn't find them, it will give an error. So there's a flag to turn off this error so that it skips trying to look for these files. So if we scroll down inside our aflow.in file, you can see here this AFLOW_AEL calc is switched on. And then you can see so then let me go back to the slides for a second. And then we'll discuss the different input parameters. So again, like I said, it's run by including the following line. So that the default AFLOW.in file will have this line commented out with a hashtag before it. So if you delete that hashtag, then it knows it's an AEL calculation. So then you have the number and size of the number. So some of the important parameters you can set is the number and the size of the normal and shear strains. So if you want to do smaller or larger strains, for example, you can adjust this strain step. The other important parameter here is that you can there's also an option to reduce the amount of independent directions by including this line here, the strains_symmetry equals on. So this is usually switched on by default. So for example, in this case, we have a rock salt structure. This is a cubic structure. So therefore the X, Y, and Z directions are all the same. So you don't need to do all these calculations separately. So instead, what will happen is that AFLOW will use this AFLOW sim module that Dr. Hicks was showing, see that it's a cubic structure and say, oh, we don't need to do each one of the different directions. We only need to do one direction and then the other directions. And then we can generate the full elastic tensor just from a smaller set of strains and a smaller set of calculations. So this just reduces the amount of total calculations that you have to do. And again, if you switch this to off, you can then do the calculations in each of the three directions. And this is useful if you want to check if you have errors. So you can check, so you can make sure that the calculations in all three directions are giving you the same results. And you can get a feel for what the size of the numerical error is. Okay, so then if you want to run, once you have your AFLOW.in file, if you want to run it, including DFT calculations. So you won't be able to do that here on the virtual machine because we don't have access to VASP. But you can run the calculations for all of these strain structures and all of the subdirectories using this command here. So it's AFLOW --multi. So what this will do is it'll tell us that it'll see. So what happens when you run this command, first thing it'll do is it'll read this AFLOW_AEL. This means it will set up all the subdirectories for the different strain cells. And the --multi tells it to go into each one of these directions in turn and calculate do the DFT calculation inside. Then once the DFT calculations are finished, you have to rerun AFLOW to do the post-processing. So the easiest way to do this, if you're running on a cluster, is just to include this line twice in the submission script. And in between, you're going to have to change the name to the lock file. And we'll sort of go through how to do all of this. Okay, so we have so we have a set of exercises. So the first one is to make a copy of the MGO directory in the 07 underscore Thermomechanical 1 underscore AEL directory, and comment the appropriate line to run an AEL calculation in the AFLOW.in file and rename the lock file. Okay, so can I run? Okay, so can I run only analysis from pre-calculated data, and can I restart a calculation from where AFLOW will detect? So there's a question in the chat. Can I run only analysis from pre-calculated data, and can I restart a calculation and AFLOW will detect whether the run terminated previously? So the answer is yes, up to a point. So for if you have everything is pre-calculated, and if you want to rerun the post-processing, that's fine. So like not so much, it's probably not so much interesting for AEL, but certainly for if you do the thermal properties, if you have all the energy volumes calculated, and let's say now you want to change, let's say the temperature range that you want to run over, you can rerun a post-processing, changing the temperature range or changing this temperature step. So you can do these kind of things and change this at the post-processing stage. And this is something we've done before, actually. Assuming that you have enough energy volumes to actually get a good enough fit that will actually go up to the higher temperature, if you want to do a higher temperature, for example. Restarting a calculation, it'll detect which subdirectories have already been run. This is done using this lock file that I'm going to talk about now in a second. So if there's a directory that doesn't have a lock file in it, it will restart and rerun inside that directory. So if you just restart the calculation, it will just go and see which ones don't have lock files inside and start running those. Now, where there could be an issue is if there's a calculation, like a VASP calculation that didn't finish completely. So what will happen then is that AFLOW will run to try and run the post-processing, see that file has a lock file inside, but no outcar file. So you'll get this error message warning you. So you have to go in and delete the lock file, then rerun AFLOW, and it'll then rerun that particular VASP calculation that's missing. Hopefully that's clear. Okay, good, thanks. Okay, so that's the first exercise. So again, we'll talk about the importance of this lock file. Okay, so then if you want, so then once you have this lock file, then you can use this command to run the generate AFLOW in to AFLOW minus run equals 1 minus generate AFLOW generate underscore AFLOW in underscore only to create the subdirectories for this AEL calculation. So this flag, we only need this flag at the moment because this virtual machine, we don't have access to VASP on this particular virtual machine. So if you try to generate all these subdirectories, well, once you run AFLOW and it's looking inside an AFLOW in, the first thing it's going to do is try and find, one of the first things it's going to do is try and find the potcar files, so these pseudo-potential files that are specified in the AFLOW in directory, in the AFLOW in file. So it's going to search through a set of default directories. And this is one of the things you can add to your AFLOW RC file, is where these directories are. So if you want to set this up to run on your own system, you can add the path to your own potcar files if you have access to VASP on a particular cluster. Okay, but adding this flag tells it to skip this step so it won't throw an error, and it'll just generate the AFLOW in file. So this is mostly just for teaching for this purposes. Now, if you do want to run the DFT calculations, you should use the command AFLOW multi -d. So -d just tells us this directory. This isn't really necessary. I usually like to add it just to make sure that it does actually know which directory to run in. So just, okay, and then to check, okay, but once you generate these files, check how many of these subdirectories are created. Then make another copy, and at this time switch the option to control use of symmetry, determine the number of directions to off. So you have this strain underscore symmetry, and you switch this to off, and then we run and see how many directories are created. And then finally, in this other directory, mg underscore AEL AGL, check what output files are generated by AEL. So this is some of the output files that are generated. So this is from a previously run AEL calculation. So then you can see what the output files are. And this main output file is what's called aflow.ael.out. So if you look inside this, find the different bulk and shear modulus, J, and the Poisson ratio for this material. Okay, so before we split into our groups and go into our breakout rooms, I'm just going to show you quite briefly what I mean by renaming the lock file and these sort of things. And talk a little bit about the lock file because I'm not sure if we discussed it too much yet, but it's quite an important thing to know about if you do want to run, especially if you want to run DFT calculations with AFLOW. So here we go to 07 underscore Thermomechanical. So day 4 under 07 underscore Thermomechanical 1 underscore AEL. So here we can see our directories. If we go to MGO. So if I was to just try to run AFLOW in this directory, what would happen is I would get this error. Well, not error, but this message. So AFLOW, no more subdirectories to run. And this is because AFLOW found this lock file inside this directory. If it sees this lock file present, it knows that this directory has already been run. So the lock file, the file with this name lock, tells it the directory has already been run. It doesn't run this rerun this directory. So this is something that, especially if you're doing lots and lots of automated calculations, you want to make sure you don't accidentally overwrite the calculations you've already done. So this, you can sort of let this go and you don't have to worry about overwriting existing calculations because of the existence of this lock file. But if we do want to perform calculations in a directory that's already been run, then we have to get rid of this lock file because this is present. This will prevent anything from running. So we can either delete it if you don't mind losing it, or we can just say change the name to something like AFLOW underscore lock, AFLOW lock.11. There's also an option called --use underscore lock equals, and this allows you to specify a different lock file name for this calculation. Okay, so Corey's opening up the breakout rooms now. So yeah, but just wait till we go in because I just want to finish showing you these examples so that we can set up and give him some time to actually assign everybody. Okay, good. Okay, so we've renamed our lock file. The other thing, I'm just going to run through the first exercise so we see what things we have to do. We go into the AFLOW.in file. Here we can see that this is actually a standard AFLOW.in file. This is for a normal DFT calculation. Okay, so this is something that's where the relaxation has already been run. I don't have all the different directories here, just to save space on the virtual machine, to make it easier to copy files back and forth. But if you look down at the bottom here, one of the things that you can see inside this AFLOW.in, you see where it says self-modification, recycling concar of relax 1. So this is the relaxed structure from the first relaxation run, and this is the one from the second relaxation run. So here we actually have the relaxed structure. And because AFLOW always reads the AFLOW-in from the bottom up, it will always take the most relaxed POSCAR, so the most relaxed structure that's at the end of the file. So in this way, you can basically reuse an AFLOW.in, so from a relaxation to then run something like an elastic properties run or a Debye-Grüneisen run, or maybe the phonon calculations run that Dr. Estes and Dr. Smoljaniuk will be showing you tomorrow. Okay, so we can see that because this was an AFLOW.in from a relaxation run, you can see that this AEL here is commented out. So now if we want to run, now we have our relaxation performed, so we have a relaxed structure. So now we want to calculate the elastic properties of this structure. We then uncomment this option here. So we delete the hashtag, and this gives you, now the elastic constants are switched on. And then if we can, now we should be able to use our command minus. and hopefully it will run. So now it's working out the strains, creating the matrix, and now it stops because you see it sees that the lock files are missing in the subdirectories. So now it's going to, so if you run this normally on a cluster with VASP, it will say stopped, waiting for completion of required calculations. And then it start running AFLOW in each of the subdirectories and start doing the VASP calculations for the strain structures. Okay, so you can see it's generated structures here. Okay, so let's see if everybody has been assigned to breakout rooms. Yeah, looks like everybody.
Yeah, we should be all set.
Yeah, okay, thanks. Okay, so everybody's assigned to breakout rooms, so we can go into our breakout rooms now for, let's do 10 minutes. So that would be, it's now what? It's now 15:10, I think, in Germany. So if we want to meet back here at 15:20, so let's do 10 minutes for this exercise. And we meet back here in 10 minutes. Okay, so we can go into our breakout rooms now. So the first question is to make a copy of the MGO directory and then comment the appropriate line to run an AEL calculation, rename the lock file. I'm not going to bother making a copy, but we already kind of went through this. These, and I'll delete these lock files here. So what we should have done was uncommented this line. It says AEL_AEL calc. Let me reset this. This was strain symmetry on. If we run like this, we see that we form a total of 8 subdirectories. So here, these are sort of numbered 0 to 7, sort of 8 directories. Then here, after this SF, so FS here stands for strain factor. And then this tells you the type of strain that's been applied. So in this case, this is a normal strain that's in the first independent direction. That's a 0.99. So that means it's a 1% compression. Here so all of these strains, so all of these ends are in the are normal strains. Here you can see that's a 1% extension, for example, for this one here. Then we have the S is the shear strains. Again, you can see it runs from a 1% compressive strain to 1% extension strain. So then if we remove the lock file, and now we go in and edit the AFLOW-in file. Now we want to switch off this strain symmetry. So now now it won't use the fact that it's cubic symmetry to reduce the number of calculations. So now you can run. Now look, let's see how many it generates. Okay. So now you can see it's gone from 0 to 24, sorry, 0 to 23. So we have our 3 different independent directions. So here we have our normal strains. Let's see, so here we have normal strains. And here you can see the first direction, second direction, third direction. Then we have our shear strains, again, first direction, second direction, and third direction. So being able to turn off this strain factor can be quite, strain symmetry option can be useful if you want to check for things like errors. Because the 3 different directions should be the same, you can actually see just how much numerical noise you're actually getting in your calculations. Okay, so here's a calculation that was run earlier. So again, this doesn't show all of the output files, just some of them, but it does show all of the specific AEL output files. So you have things like the compliance tensor, this is the elastic constants or the stiffness tensor. You have the elastic constants in JSON format. And then this is the main output file, this AFLOW-AEL.out. So let's open up this file and take a look. AFLOW-AEL.out. Here. So we can see here we have our Poisson ratio, the Voigt and Royce approximations to the bulk modulus, the Voigt and Royce approximation to the shear modulus, the VRH average. Then you have the other things like the Young's modulus and the VRH average, which is calculated from a combination of the bulk and shear moduli. You can also get the speed of sound, the Pugh's modulus ratio, which is the ratio of the shear and bulk moduli. So this is a measure of the ductility of the material. You also can estimate the Debye temperature because we have a bulk modulus. And finally, you can also see that it's also possible to apply a pressure, but this is not something we're going to go into here because it's quite difficult, because it's a bit tricky. That's something that's sort of still experimental, hasn't really been properly published yet. Here we have the stiffness tensor. So you can see here, because this is generated just from a calculation in one direction, you can see that these are all the same. And they expect them to be more or less the same. If you were to switch off the strain symmetry and do the full set of VASP calculations, you would see some small differences here, but they will be, in general, if the calculation is converged properly, it should be quite small. It's maybe a fraction of a gigapascal. So this is another thing to notice, that all the unit quantities here are written afterwards. So these are gigapascal, meter per second, and Kelvin. And these values down here are all in gigapascal as well. So these are the these are the normal components, these are the shear components, and you can see here, these are 0 and 0, and this is what you expect for a material with cubic symmetry. Okay, so that's the AEL, the AEL part of this workflow. So now I'm going to go on and we're going to move on to the AGL. So this is the Debye-Grüneisen model. So again, the AEL is run by doing this line, this AFLOW_AGL calc. Again, we can control the number and size of the strains that are applied. So the number of structures, then the strain step. Again, the default here is 28. The default here is 0.01, so 1% strain step. Then you can also set by hand the value of a Poisson ratio you want to use, if you want to use a specific value. Alternatively, you can use the AEL value, so the value that's already been calculated from an AEL workflow. And if this is included, an AEL hasn't been run yet, the AFLOW then knows to run AEL first before it tries to calculate this. And again, you can do the full set of DFT calculations using the AFLOW ---- multi command. And this will automatically descend down into all the subdirectories and run all the DFT calculations. So again, we have a set of exercises for this. So it's very similar. So again, in the 07_Thermomechanical/2_AGL directory. So uncomment the appropriate line to run an AGL calculation, and also rename the log file. So use this command again. So again, this -- generate _AFLOW_only to run the subdirectories and see how many are formed. Check which ones are created. Okay, this time, next one is you go in and you switch this option to use AEL to calculate the Poisson ratio to off. And now then you rerun again and see which subdirectories are created this time. Finally, in this output directory, so it's MGO_AEL_AGL. Check what outputs files are generated by AGL and find the values of the Debye temperature and the lattice thermal conductivity in the file AFLOW.AGL.out. Okay, so now if we want to go back into our breakout rooms, let's take about another maybe 10 or 12 minutes. So we come back at, it'll be 3:45 German time, so 15:45, I think. So yeah, so let's take about 12 minutes for this. So if we go back to our breakout rooms, And then we'll meet back here to wrap up. Okay, so here we have our exercises. So the first one, again, is to uncomment the appropriate line to run an AGL calculation and rename the log file. So let me just go back in and look what I did before. Okay, so we go into our AFLOW-AGL file. Okay, so let me reset this. Okay, so we've uncommented our AFLOW_AGL calc line. So now we can run to generate our directories. And now what you'll see this time is that we're actually not generating our AGL directories, and you might have expected, but rather we're generating our AEL directories. That's because we have switched on the option to use the Poisson ratio. So therefore, it's going to say, oh, I need the Poisson. It still says, oh, I need the Poisson ratio, and then it calls AEL. So it runs AEL first to get the Poisson ratio. Now, if we switch off this option to run the Poisson ratio, so we remove this files, then we go inside AFLOW file. So it's going to use whatever so when it sees this option here, AFLOW_Poisson_ ratio equals on, it stops running AEL and it goes instead to run AEL. So even though this is switched off, it sees this is switched on, so it starts running AEL and it uses whatever parameters are set for AEL to run the AEL calculation. Now if we go and we switch this off, then it's going to assume a default Poisson ratio of 0.25. So this is in the value. So this is a value that's sort of the ideal Poisson ratio. So if a material responds, so basically if it's sort of like the constant volume Poisson ratio. So the Poisson ratio is basically when you start stretching material in one direction, how much does it contract in the other two directions? And if it's contracting it in the other, if the total volume remains the same, so it contracts in the other directions as much as it stretches in the first direction, then you get a Poisson ratio of 0.25. So that's sort of like a reasonable approximation for most materials. Most materials are usually normal materials are in the ratio of 0.2 to 0.3. So now we have our Poisson ratio switched off. So let's see what happens. We run it this time. So here we generate everything. And here we get all the, now we get the AGL directories. So you can see that here again, we have the strain factor. So this is like what the percentage strain. So how much it's been stretched or compressed. And here we have again, we have the log file. Sorry. Yeah, again, and here again, we see that we go from 0 to 27, so we have 28 total files. Now, if we want to look inside MGL, let's go AEL. So here now we're going to look at the output files. So here we have all the AEL output files we had before, when we also have the AGL output files. So for AGL, we get some additional data, so things like energy volume data. You can get the Gibbs free energy as a function of pressure and temperature. So this is a very big file, but it's useful if you want to try and generate phase diagrams, for example. But the main output file again is this AFLOW.AGL.out. And here I'm going to open it with VI. I'm not going to XCap because it's actually quite a long file. So here at the top, we can see, so here we have our main values. So these are things like the lattice thermal conductivity at 300 Kelvin. And this is, again, the units are here. So this is watts per meter Kelvin. We have things like Debye temperature, acoustic Debye temperature, the Grüneisen parameter, heat capacities, again at 300 Kelvin, thermal expansion at 300 Kelvin, bulk modulus, vibrational free energy, vibrational entropy, all at 300 Kelvin. And here it also tells you what Poisson ratio is used. So this Poisson ratio source, so it tells it that it was the one that was calculated by AEL, and this was the value that was used. Then you can also see further down, you see you get the different properties of function of temperature. So again, thermal conductivity, things like heat capacity and thermal expansion, and bulk modulus. If we scroll down a bit, here you can see, then we have energetic properties. So we have things like the Gibbs free energy, vibrational free energy, internal energy, and vibrational entropy. Again, as a function of temperature, so both per cell and per atom. And then just before we wrap up, I'm just going to show you inside the log file. So this is a log file that's actually from a completed calculation. So if we scroll down through it, we can see some interesting things. So this is mostly at the start when it's just finding all the different space group information. So it's working through the space group. We see all the output for that. And then we come here. So we see now, because we're running an AGL calculation at first, it runs AGL. So then here, because you see it's reading in that use AEL to calculate the Poisson ratio is 1, so that means it's on. So then you can see it says down here, it says starting elastic constants run. So it starts with AGL, it sees that it has to do the Poisson ratio, so it goes inside to run AEL. And then it sees it has a lattice cubic symmetry, so it knows number of strains. Sets up all the strains, so this is writes out the different, this is a matrix, these are the strain tensors. So here it sets up the runs. So here it creates all the files. And then it reads the information. So here it fits the stress strain data. Here it's calculated the elastic tensors. And here's something that's quite interesting, quite important. It writes out the eigenvalues of this stiffness tensor. So one of the things it'll do is it'll check if any of these are negative. If any of these are negative, it'll write a warning to say that the material is mechanically unstable. So everything is okay. Now we have our Poisson ratio. And now we can start our AGL calculation. So it goes back, you can see now it goes back to AGL. So it says AEL is successfully used to calculate Poisson ratio, gives you the value. And then it goes through the AGL, generates the strain structures, calculates the energy and volume of everything. So by reading it from reading in the data. And then it starts doing the different temperatures. So it starts fitting for each temperature. So then there's a lot of information here. I'm not going to go through it all, but for each temperature step, it writes out like the fitting procedure. Results of the fitting procedure, what minimum volume it gets, and so on. Okay, so that's pretty much everything for the AGL, so the thermomechanical properties. Dr. Esters will be up next talking about the database and the data APIs. So unless anybody has any additional questions, we can take a break, 15-minute break. 15, maybe 20-minute break. And yeah, I'll hang around for a few minutes to answer any additional questions. Do we get plots? So by default, the plots themselves are not actually generated, but a lot of this information here can be used to generate plots. So it's something that there are options. I think I haven't used them in a long time to automatically generate some of these plots, but so that's why all these additional, let me share my screen again. that's why these additional files are printed out, because say, for example, this AGL underscore energies underscore temperature file. So if we look inside, this file, energies. So you can see this is written in a format that's actually quite easy to plot. You just have temperature here, and then you choose which one of these columns you want to plot against as function of temperature. You can do something similar for thermal properties. So again, let's say you wanted to let's say, heat capacity at constant pressure as a function of temperature. Then you just choose again which two of these columns you want to do. And because these are all commented out, at least for a lot of plotting functions, they'll know to skip all this and just to plot the two columns you specify. Okay.